Welcome to the Explainer. Today, we're breaking down a tool that's absolutely foundational to data science, but here's the catch. It's also one of its biggest potential pitfalls. We're talking about the powerful, yet so often misunderstood, linear regression. All right, so let's get right into it. You see linear regression everywhere. I mean, in analytics, machine learning, you name it. But here's the thing. Using it the right way, that's way harder than just plugging in some numbers and hitting go. Its simplicity is super deceptive, and if you get it wrong, you can end up with conclusions that are just, well, completely flawed. So you see this equation, right? It looks so clean, so elegant. You might think, hey, this is pretty straightforward. It's kind of like looking at a perfectly built house. But what's really interesting and what most people miss is the foundation it's sitting on. The whole thing, all its predictive power, it all depends on a set of rules that honestly get ignored way too often. So let's start there. Let's unpack why this model is so incredibly popular, but at the same time, so frequently misused. What makes it our first choice? And what are the deep complexities hiding just beneath the surface? I mean, its appeal is obvious, right? It's simple to get your head around, it's super interpretable, which just means you can actually explain what all the different parts of the model are doing. And it's fast, like really fast to run. Put all that together, and you've got the perfect go-to for when you're first starting to explore your data. But, and this is a huge but, to get those results you can actually trust, the model has to stand on some really crucial pillars. These are its core assumptions. And think of it this way. If even one of those pillars starts to crack, the whole structure can become unstable. Okay, so here they are. These 7 things are basically the mathematical rules of the road. They're what makes sure your model's conclusions aren't just fantasy, but actually reflect reality. Now, we're not going to do a deep dive on all 7 today, don't worry, but we are going to look at a few of the most critical ones, the ones people forget about all the time, just to show you why they are so important. First up, and probably the most fundamental one, is linearity. The model is built on one simple idea, that the relationship you're looking at can be described with a straight line. That's it. It assumes a straight line is a good fit for the trend in your data. Okay, so what happens if it's not a straight line, right? What if the relationship is actually curved? Think about something like disease progression or financial growth. Those things often follow an exponential pattern. So what's the big deal if you try to force a straight line onto something that's clearly a curve? Well, this is exactly the problem. When you do that, when you force a linear model onto a nonlinear world, you get predictions that are just plain biased. The model consistently gets wrong. It underfits the data. It can't explain what's really going on, and at the end of the day, you just can't trust the conclusions. They're basically worthless. All right, next up, we have a word that's a real mouthful: homoscedasticity. I know, it sounds super complicated, but the idea behind it is actually pretty simple. All it means is that the spread of your data points around that regression line should be pretty much the same from one end to the other. And here's another huge one. You've got to avoid something called high multicollinearity. You want your predictors, the things you're using to make a prediction, to be independent from each other. If they're too similar, like say you're trying to predict someone's weight using both their height in feet and their height in inches, the model gets confused. It can't figure out which variable is doing the work. Their effects get all tangled up, and your results become unstable and totally misleading. So, let's talk about when that foundation cracks. What are the actual real-world consequences when you just ignore these rules? Because this isn't just some academic exercise. This has a serious, practical impact on your results. This quote from our source material really nails it. We're not talking about your model being off by a tiny little bit. No. When you violate these assumptions, your entire conclusion can be flat out wrong. And that means you could be making some really bad decisions based on totally faulty information. So here's a classic red flag. If you plot your model's mistakes, its errors, and you see this funnel shape, that's a huge sign of trouble. That's called heteroscedasticity, It's the opposite of that big word from before. It means your model is way less accurate for some of your data than for others. And why does that matter? Well, it completely invalidates all the statistical tests, like p-values, that you use to prove your results are actually meaningful. Okay, but let's say you do everything right. Your foundation is rock solid, you've checked all the assumptions. Even then, the house you've built has its limits. There are just some jobs that linear regression was never, ever designed to do. And a perfect example of this is the outlier effect. You see, linear regression is super sensitive to them. All it takes is one single extreme data point, and it can act like a powerful magnet, literally pulling the entire line towards it. And just like that, your model is completely misrepresenting the real story that the rest of the data is trying to tell you. And this table really drives the point home. Sometimes, linear regression is just the wrong tool for the job. It's like trying to use a hammer when you need a screwdriver. If you're trying to predict a yes or no answer, you need logistic regression. If you're working with data that's a count of something, like how many times a customer bought a product, you should probably be using something called Poisson regression. Using the wrong model isn't a small mistake. It's a fundamental one. So, okay, after all this talk about assumptions and limitations, you might be thinking, so, is linear regression even useful anymore? I mean, in a world with fancy, powerful stuff like neural networks, where does this old school model fit in? Oh, it's not just useful, it's absolutely essential. Think of it as your baseline. It's the first thing you build because it's fast and, most importantly, transparent. You can understand exactly what it's doing. You set that benchmark, and then you bring out the big guns. And you can ask, is my super complex black box model actually doing any better? Or is it just adding a bunch of complexity for no real gain? And that really brings us to the main takeaway, the single most important point of all of this. Build responsibly. Look, the real power of a tool like linear regression doesn't come from knowing which buttons to click or which line of code to write. It comes from understanding its foundations. It's about respecting its rules and knowing when it's the right tool for the job. And, maybe even more importantly, knowing when it's time to put it back in the toolbox and grab something else. So I'm going to leave you with this one final question to think about. The next time you build a model, before you trust its output, before you bet your job or your company's money on it, ask yourself this. Did I check the foundation? Is this model reflecting reality? Or is it just a house of cards, built on assumptions I never even bothered to test?